So hi everyone. Today I'm going to be talking about this spectral audification approach that we've been developing as a way to investigate astronomical data cubes. So data cubes are a form of hyperspectral data where down every pixel of an image, which could be a field containing a galaxy or a star or some other astronomical object, down each pixel we have an entire spectrum of information. So this data can of course be really rich. It can also be pretty unwieldy and hard for humans to inspect. So in order to build this human intuition, we've been developing a way of using sound to communicate the spectral dimension while we can project the two dimensions that are spatial on our screens. So in this way, we can use the fact that sound is very naturally represented using a spectrum. We can just basically take a processed version of the spectrum down each data cube, and by using a inverse Fourier transform, we can generate a sound signal. So this can be particularly clear in examples like galaxies with emission lines, because these emission lines, effectively something like a delta function, a narrow spike, translates to something like a sinusoidal wave, a pure tone. So if you have multiples of these different emission lines, you hear combinations of tones that are telling you about the different spectral lines that are present down a particular spaxel, for example. So if I click on this field, which is an active galactic nucleus taken with the MIRI instrument from JWST, you should be able to hear two tones in this particular spaxel. You're hearing a low tone and a high tone. But as I move around, for example, here you hear a third tone come in. Here you hear some noisy feature, as well as this lower tone. And these can often be hard to spot, but our ears are very good at picking them up. So if I use a log scale, maybe you can see a bit better. The idea is that this is clearly kind of rich data, but by using sound, we can use our pitch sense and our pitch memory to track and notice different tones as they appear and disappear, telling us about the presence or absence of different lines. We envision this as an efficient way of exploring these cues because you can move around quite quickly and hear different features pop in and out. So if I'm listening for a particular tone or a particular combination of tones or a particular sound that represents some physical property of the spectrum, I can pick up on these quite quickly and then hone in and explore them. We're hoping that by listening to data cubes in this kind of way, we might be able to pick up new information or get new insights into them. So this is one regime where we're listening to a sort of broad spectrum that might have multiple spectral features in it at the same time. We can listen to them emerge and disappear. But another thing that we could do with this approach is listen directly to the kinematic or dynamical structure of a galaxy. So to do this, one thing we could do is zoom in on the spectrum around a particular line. So this one is at around 10.7 microns. So if I zoom in on this one, I pick this wavelength range and I can generate the audio cube. So zooming in on this line, so now you can see that the integrated spectrum just shows a much more compressed, a much zoomed in version of the line where we're listening to the line around this, the wavelengths around this particular line. And I can see how this changes. And you can hear the sound as I move my mouse. If I click and hold and move my mouse around this field. So listening first to the center, you hear this kind of windy sound that's representing all the frequencies associated with this line profile. As I move to one side, you hear it. It's lower pitched here. This is because this is lower frequency light. This line has been shifted to lower frequencies. So you can sort of directly hear this Doppler effect using sound. This is receding from us, so it makes a deeper sound. You can hear that this is higher pitched on this side. So you can hear a higher tone. And you can also just inspect more generally. So you can hear, for example, here that this has maybe two components, one that's approaching us and one that's receding. We can explore and basically directly listen to the kinematic structure of this object in this way. The general idea with this kind of listener, while we have these two cases in mind, is to inspect how it can be useful. So we're interested in people with different data cubes and different forms of data and trying to do different tasks or understand different things about the objects imaged in this way. And we're interested in how sound or spectral audification can help.